All right. Hopefully people on Zoom can hear me. And everyone here, welcome back. So today we have a hands-on session using Orvara, which is an orbit fitting code on GitHub. I know some of you have used it already. Our hope is that it's useful to as many of you as want to play with these data. So the session today is pretty boilerplate. It is number one on the sheet that you got, where you just install the code. Hopefully, many of you were able to do that already. I know there were some issues, annoying ones with especially Windows computers. I think there were issues with GCC versions, something with character encoding in PTMC, annoying things. Hopefully, most of you have been able to overcome those. If not, we should have it on a Colab notebook. So hopefully you'll be able to start either with a Colab notebook or with the code installed on your personal machine. So I do have it installed on my personal machine now. And I'm going to share my desktop. Okay. So I'm not going to go into the guts of how the code works. There is a paper for how the code works, and if you are interested, there is also a YouTube video where I go through that paper with the editor of the Astronomical Journal. So I will put that in later. Okay, I can. Okay. If you have this installed, then you interact with it through basically just two commands, fit_orbit and plot_orbit. And everything that you need to do comes in something called a configuration file here. Here is an example configuration file. I copied this from the tests directory of Orvara. So let me go in here. And I will put the exact link to what I'm using. Oops, not that. Here. So all of you can see exactly what it is that I'm using and modifying. So I'll briefly go through what some of these things do, so that you can then modify them to use them yourselves. This first one is the Hipparcos ID of your star. You'll generally know this. This is so that it can look up the absolute astrometry from the catalog file. This you probably won't need to change, the Hipparcos Gaia catalog file. You then have these files with the data for your object, and they need to be in a specific format. I believe that we have given you all of the data files that you need, or they are in the appropriate directories. So you can go through those and you can see what the format is, what the units are. If you get the units wrong, it'll get very confused. It'll try to fit meters per second instead of, or it'll try to fit kilometers per second instead of meters per second, things like that. I am not going to give it a start file here. The start file is if I wanted to converge faster, then I give it a starting position that isn't whatever Orvara's default is that I set some time ago. Orvara is a Markov chain Monte Carlo code. I don't know how familiar many of you are with Markov chain Monte Carlo. Essentially, Markov chain Monte Carlo is a way of avoiding having to do a horrific integral. If you can do an integral, that's what you would want to do. But you have some likelihood function where an orbit fits well or it doesn't. And you can write down the probability of getting your data given that orbit. That's called a likelihood. It's closely related to chi-squared. What you want to do in order to infer parameters is you want to take that likelihood and you want to normalize it so that you can treat it as probabilities of all of your parameters. The problem is that if your likelihood is in a high dimension, normalizing it means doing a high dimensional integral, and high dimensional integrals are hard. That's the reason we turn to MCMC. In some sense, it's admitting a failure at the outset that I can't do the integral. Therefore, I have no choice but to go for MCMC. So it's not something you reach for as a first resort. You reach for it when you cannot do an integral for a good reason. If you're trying to explore just a couple of parameters, you could probably just do the integrals. But in this case, the number of parameters for fitting an orbit is pretty high. And an 8-dimensional integral, for example, is intractable. So one of the things that we'll be looking at in this hands-on session is whether I am converged in my Markov chain Monte Carlo. What it does is it's a guided random walk through parameter space. You randomly step around and you let your walk be guided by how likely different parts are. I propose a step and I decide whether or not to take it depending on how much better or worse that orbit fits the data than the orbit that I have now. When all of your different chains are wandering around the orbital parameter space and they've gotten to the same point, that's when you can stop. You're never going to be able to prove that you have converged. It's not possible. And so there are going to be cases, including in the literature, where Markov chain Monte Carlo analyses have produced an answer, but it's incomplete or not correct because it has not converged. That's something that we're going to learn how to watch out for here. These are settings in the Markov chain Monte Carlo. I have these set to a couple of values now so that the chain will run very, very fast. I'll run it with these. It'll take a few seconds, and then I'll run it again with longer ones soon. And you guys will be able to do the same things. You can support multiprocessing on certain computers. Don't worry about that too much. And then this, use epoch astrometry, is whether you want to fit the sky pass within Hipparcos and Gaia using the individual scans, or whether you want to use a polynomial approximation. A polynomial approximation should usually give you basically the same answer, and that means setting this to false. These other parameters here, we won't worry about for now. Some of these will be relevant in the hands-on sessions tomorrow if you want to try to fit some systems that are a bit trickier. This is going to be the important thing to plot my answer. But before I do that, let me run it. So I'm going to be in my Orvara root directory. Here I am. I'm not going to type ls because this directory is a mess. You don't need to see that. And I'm going to run it by just doing fit _ orbit. And then I'm going to type the name of the configuration file and enter. That's all you should need to do to run it. It's going to output a file in the directory that you are running it from. If you wanted to output a file somewhere else, you can use the --output-dir option. I'm just going to dump it here for now. I'm going to press enter. And let's see. This one gives you a nice warning that there was a bug in the Hipparcos 2 intermediate astrometric data for this source that it's trying to fix. Don't worry about that. We don't need to worry about that warning here. And this is running very, very fast because I didn't ask it to do very many points. It's done. So it wrote this file right here. It will not overwrite a file, but it will come up with a new one whenever you want, whenever you run it again. And that file will save your information to the header so that you can access whatever it is you use to make the file, whatever parameter settings you used. I'm now going to tell it which data file I want it to use. This one. And so now I'm going to interact with this in the other, with the other command that we typically use, plot orbit. Here. And that's going to make a series of plots to visualize the chain. Oops. And I asked it to discard the first 100 steps at burn-in, but I didn't even save 100 steps. So let me ask it to just discard the first one as burn-in. And now it should spit out some files. So hopefully you guys will be able to run those two commands on at least one of the initial targets. That's goal number 1 for today. Goal number 2 for today is to take a look at these plots and interpret some of the things that you're getting. So there are these diagnostic plots. For example, here they are. You can see some of the ways that Markov chain Monte Carlo works here, where you have the various different chains, and they're bouncing around looking to see what the best orbit is. Here, they're getting the secondary mass. It looks like they're getting about 36, 37 Jupiters. This one is converging very, very, very quickly. But notice how at the bottom, it starts out at a lower probability and then ramps up to a higher probability. This is a log probability here. And so the difference between -1200 and -1150 is 50. The difference in likelihood is a factor of e to the power 50. So you want to make sure, in order to be converged, that all of these lines are clumped up together and that you don't have certain chains that found a better orbit. You don't want to be stuck in various local minima. That is a classic way that a Markov chain Monte Carlo result fails and is not converged. The other way is if you never find the global best fit set of orbits, family of orbits. That can also happen. You get stuck in a local minimum, you never find the one that you actually want. That can be extremely hard to guard against, and it's something that professionals struggle with all the time. So it's not something to feel bad about if you struggle with it too, because I do, I think we all do. Okay, so it looks like discarding 1 for the burn-in wasn't enough. If I want my chains to be possibly burned in, I'd better discard some more. I can do that, and then I can remake the diagnostic plots. Let me just discard 5 because I didn't save very many points here. And so then you'll see after I discard the first 5 that things will hopefully look a little bit better. And then there are examples of these included with your in your PDF file. And that looks better. These different lines, maybe they're still trending up a little bit. And again, I only have a few points. I'll run a much longer chain soon. But things seem to be starting to settle in. And if you run a longer chain, you'll be able to see whether they have settled in or not, hopefully. Okay. That is, I think, enough for you to get started. I don't want to stand here and talk to you for a long time and just go through this. So my hope for the first part of today's session, and please ask for help, is to take one or more of these objects for which we have everything basically ready to go, for which we have a configuration file, an RV file, an astrometry file. Open them up, take a look at them, and see if you can run them and make diagnostic plots. I would suggest that you start with a low number of temperatures and a low number of steps so that it runs quickly. This took 10 seconds or something. And then if you want to take a closer look, then let me run it a bit longer, and this will take a couple minutes. You can run a longer one, but not so long that it takes half the session. So something like 10,000 steps, I think, would be appropriate for now. You can probably see my progress bar that this is going to take something in the range of, I don't know, 3 minutes. So that's my goal for now. And then if you want to continue playing with Orvara tomorrow in the group projects, then you can choose one of the exercises in the second part of the PDF that you should have. Or you can, I suppose, make up your own. And then there's also the project to actually fit the individual epochs of fake Gaia data. And so I'd also be happy to discuss some of that tomorrow. That project for tomorrow is going to require a bit of familiarity with linear least squares fitting. So if you have some degree of comfort with linear least squares fitting, that'll help an awful lot in tackling that particular project. So I'll let this go. When it is done, I will make the plots and I will show you what they look like. But I think that other than that, I'm happy to shut up and let you guys start playing around with it. If you finish the first part today, you might be able to do that. It's hopeful, it's intended to be fairly canned. Then please feel free to move on to the second part. And I think hopefully you all have that PDF of all of the different exercises that you can do with Orvara. I will say that the first exercise, the one for today, has solutions that you can look up in published papers where I'm pretty confident that those solutions are correct. Many of the exercises for tomorrow do not have published solutions. And so in that sense, they are more open-ended, and we'll let you play with some of the vagaries of fitting and some of the things that maybe you would make a different choice from the people who published the paper, and those different choices I think would be perfectly defensible. So you can play around with that tomorrow if you are so inclined. So I think that's all I wanted to say. And me being unfamiliar with exactly how this works, I don't know whether we want to raise hands or if people want suggestions or input. We have a number of helpers in the room. If you are a helper, do you have people stand up? And then if the and then if the question has something that comes up a bit and it makes sense to just talk in front of the whole group, then we can certainly do that. The remote attendees. Okay. Yes, thank you. And I was reminded to say, thank you, that the remote attendees, if you would like to ask questions, please do so in Slack. We have a number of helpers who I think will be focused on the Slack help, in addition to people who are focused more on the in-person help. I'll leave the screen share up for the moment, and then I'll show you what these files look like for me. Yeah. Questions. Okay. Sometimes I can check in with them tonight. Okay, mine is very similar to okay, good. My hope is that this is canned enough that is straightforward, and then tomorrow is more open-ended. But hopefully it'll be open-ended on the science and not on the facts. Exactly. I hope so. Yeah, in another half hour, I'll want to probably say a little bit more about convergence and when is it probably open, because that's one of the two things that you might learn. Okay, I think I actually would like to say a couple more words now, just a couple. So first, I want to give a brief overview. I should have done this earlier of the 2 goals I have for you for today, or 3 goals, 3 goals. 1, get the software to work where the mechanics are not an issue and where you can focus on the science. And then 2, when you do a fit, there are 2 questions that I want you to constantly have in your mind, trying to answer. 1, is my fit converged? That's one of the things I'm looking at here with the diagnostic plots. This fit is not converged because you see these points here that have not converged to a steady level. If I discard a bunch more points as the burn-in, where's my burn-in parameter here? Burn-in, if I do that as 100, then I think that should be enough. And it should pass that test. The second question I want you to ask about your fit is, to put it rather crudely, doesn't mean anything. In order to interpret this, Markov chain Monte Carlo is computing and normalizing a likelihood, treating it as a probability. There are assumptions that go into treating your data, the data given your model, as a probability. You need to assume that your model fundamentally includes the correct answer, in this case, a Keplerian orbit. You also need to assume that the data mean what you think they mean. If your chi-squared values, for example, are really bad in the best fit orbit, then it makes it hard to trust much of anything that comes out. So let me see. The diagnostic in this case, that looks pretty good. There is no sign of non-convergence here. So this diagnostic plot at least passes that test. All of these lines for log probability are kind of clustered together. There's nothing that seems out of whack. So and all these points also seem to be jiggling around. They aren't crisscrossing back and forth in a way that they only do once. We can then check and see, is my result a formally good fit? And the file, the code should give you a best step parameters file that will let you do a sanity check on this. Okay? So it gives you a chi-squared for separation and position angle. I think we have 4 points each. So the chi-squared that you get for a formally good fit should be something like 4. Should be a little bit less because we're using from some free parameters to fit them. But a chi-squared of separation and position angle of about 2.8, that's fine. you want it to be roughly the number of data points, actually a little bit less. If this chi-squared for separation of position angle said 50, that would be bad. That would mean that my model for 4 data points doesn't fit at all, or fits really badly, makes it hard to trust anything else that comes out of the fit. It's trying really hard to smash a square peg into a round hole, and how well that square peg fits into a round hole doesn't necessarily mean very much about your physics. So these values here, these chi-squared for the absolute astrometry, you want these to add together and just be a few. You have essentially 6 measurements here. 3 proper motions, each have 2 directions. But you use some freedom to fit the barycenter proper motion of the system. 2 degrees of freedom for that. And so those numbers, 2.6, 0.24, and 0.4, should add up to realistically something like 2 to 5, 2 to 6. They do, and so it passes these sanity checks. So that's the first question you want to ask, am I converged? Second question, does it mean anything? Are my chi-squared values vaguely sensible? If you pass both of those tests, and only if you pass both of those tests, can you open up your corner plot and take it seriously? So if I pass both of those tests, then I can open this up, and it kind of is something that I can trust. And in this case, the secondary mass is very precise, and this should roughly match what was published. Okay, so I think that's all I wanted to say. Again, just to beat it into everyone's head one more time. Aside from the mechanics of learning how to run this, the 2 questions to keep in your mind: am I converged, and what does it mean? So go for it. You can fit all these objects, and I think every object that we have for you to fit today should be able to check out where these best step chi-squared values are vaguely sensible. There might be some objects tomorrow where they're not, and you'll have to think about what that means, where the chi-squared values are poor, and that means the best fitting orbit is not a good fit to the data. All right, sorry for the interruption. Okay. Oh. There's no HTTPS. Elise? I think I can do that now. So here is the collab instructions, right? And so I want to, whoops, not that. I want to copy link address and then, yeah.
Yeah, I know where you want to put it. I
Okay.
saying I can install Orvara, but you said the other option.
Uh-huh.
Just here, I adjusted the page so it could fit that in the pictures, but
Oh.
maybe, I don't know where to put it.
That's
Um, I'd mess up
So-
the format.
no, at this point here, it's further down. Oh, I see what you're
No,
saying.
but
Yeah,
if
yeah.
you add anything in there.
Oh,
it's
yes,
gonna-
yes, yes.
The pictures are gonna fit on the page. This figure is not gonna fit on that page anymore.
Oh, I can wiggle that up a little bit. That's fine. And so
Here's, let's see, so we then
complete
another
the
option
Jupyter
is
notebook.
another option is to use Google Colab.
Or start the Jupyter notebook. Instructions for using and links to a collab notebook are here. Right?
Yeah.
Is that correct?
It's also like Colab notebooks. They use for the part 2 and stuff like this, but that's okay. We can put it in there.
Okay.
If you want to put in parentheses, which does not require Python installation, right? After not require Python installation. It's kind of the main idea.
Okay.
I'm just gonna mess up the formatting, but
Okay. And probably put that on a new line. Oh, no, it's gonna wrap anyway. All right, but Let's see if the URL still works.
Oh, wait, you have a name.
It should. Yep. Perfect. That's what we wanted. Oh, page not found.
Oh, it's a contact, yeah. It is cut off, sorry, it doesn't have the next side on.
What is it?
No, it was cut off, like when you look at the PDF again. So you say it was a new line. It just cut back, it's supposed to have introduced.
Oh, next side dot caltech.
So when you click on that, it
Oh,
make it small.
right here. Annoying.
And make a new line to write. Oh no, actually it didn't help with the PDF.
Right here.
It's still wrapping up. Oh, okay. Probably small, my board.
What?
Yeah.
Oh, that's correct. That's not a bug.
Oh, because it took it off. That's when it executes something in the shell.
Yes, yes.
Why you doing it?
Mhm.
Yeah.
Oh, perfect. Small just fits on a line. Let's see if I'll fix that later. That's fine. Does this work? Yay! It works. Okay.
Because then on the second page you have the Google Column tutorial and then to the
Yes.
Google Column for their project.
Okay. So let's see then. This is a bit messed up. I am reproducing a few of these
Is it way to make this
plots
narrow? I don't know.
here, and then I want to skip back some more.
That's good actually. Oh, no.
And I need to then just fighting with latex.
It's almost
with
like that, right? You want to do something and it doesn't do it for you. It says, right there.
it. Okay, but those aren't links now, and so I think if I just give an explicit URL link to the same one,
Okay,
then
fine.
that's probably what I want to do. That won't work with the mini page, so this time I will need to make it smaller, but that's fine. It's,
Script size and it's tiny or whatever.
Yep. I don't really want it to be tiny. Okay. Or you know what I can do? I can do footnote size, and I can do an H skip. Stupid stuff like this, right? No, it doesn't like that. You only fight so much with LaTeX formatting.
Yeah, but because I put the link that it's an instruction for Python code form. Those are my Python instructions and link to that.
Okay, it's just that if you want to find, you click on this, where do I find this?
Exactly. There's a document that you can find.
Okay. Okay.
But then it's the same thing, but this has Python instructions, but it's updated.
Wait, and so this is, so they should use a different notebook for the,
For
tomorrow?
projects,
Yeah,
we have
right.
notebook, but then for the Python, at the end. Because the tutorial, you have it in Orvara, right?
Yes.
But here, this is again, down at the workshop, we have
Okay.
you could also actually, I'm sorry, yeah. You could just provide actually this link. Because this is the SW over our project. It's sort of an empty
Oh, okay,
notebook, so
okay,
you
great,
actually
great.
just do that.
So,
I could should I email it to you?
probably it would be just as quick for me to copy it here. Cat.
That's copy.
Uh-huh,
Dot iPad dot activity.
uh-huh, uh-huh.
And yeah.
Let's see if I got it right.
Make it directly to
Yes, good.
yeah, and then you can actually you can make an HTML like about the link, right? You can just use there is use the notebook and the text with the link, right?
I wish I knew how to do that in LaTeX. I know how to make the explicit URL, but I don't know how to make a link.
I think that the URL is even
Is this the
square bracket in front and you write text. I think it will link. I don't know if that works. In
Like
square brackets,
this?
so- no, like in front.
Oh,
I can look it up, but there was a way to. No.
invalid URL command.
Okay, no. Okay, it's
Okay.
fine.
Okay. I know. Oh, you can do that in LaTeX?
Yeah, it's from overlay. Yeah, you
Oh.
do href and then you do the HTTP address and then it's always the curly bracket. So the
Oh,
first
so it's a little bit different from the HTML href command. Okay.
so
So,
href that, yeah, the yeah, exactly.
okay,
And the text would be when we have on top of the
okay.
Jupyter notebook.
It's not happy. Oh, it doesn't. Is there a package I need for href?
migration?
No. Does it say at the top that you need hyperlinks? Introduction? Use package hyperref.
Remember, it's with Python principle, right? And you have to import stuff, otherwise it doesn't work.
Yep. Beautiful. It works. Okay, I think we're good. So now it shows up as hyperlinks. Okay. So how do you want to do this? You have access to this, so you can. Yeah. 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 Thank you. Yes.
Could you explain about like burning clothing? Because most
Oh,
coming from the burning.
okay.
On the burning stuff, because they said,
Okay.
they think they set the stuff like 1,000, burning 20, but they said it's actually the border.
Oh, okay, okay, okay. Thank you. So there is a question about the burn-in and how that works. If you're all set with the burn-in, then feel free to tune out and keep going. If you've been struggling with the burn-in, then please listen and hopefully this helps. And if not, please ask questions. Let me see. I want to share my screen again. There we go. So this particular chain I ran with 10,000 steps, but I only saved every 50th one. So the chain on my computer has 200 points, 10,000 divided by 50. The burn-in is how many of the initial ones I throw away because I have not yet converged to the likely orbits. If I turn burn-in to 0, I throw nothing away and then remake my plots. Whoops, plot, there we go. I'm gonna need to reopen this. Okay, I have thrown in none, and you can see that the initial steps are really, really bad. These are incredibly unlikely orbits. Burn-in will throw away a certain number of steps. If I put in burn-in of 20, it will cut off right here, and it will only show the points after 20. So let me do that next. I'll make burn-in 20, which means it's really throwing away the first 1,000 points because I only saved every 50. So it's throwing away the first 20 of those. If I throw away the first 20 of those, so the first 10% of my chain, then, come on. It actually looks pretty good. Not quite converged, but close. You can maybe see that these probabilities have pretty well stabilized, but there's still a little bit of drift in some of these other parameters. So in order to get a better degree of convergence, I'm going to throw away an extra 50 points for a total of, let's say, 70. Okay, so the burn-in again is how many steps you are throwing away at the beginning, and it refers to the number of steps in the thinned chain. So my chain, because I'm saving every 50th point, only has 200 points long. And so the burn-in of 70 is throwing away the first 35% of my chain. I'm going to plot it and then show it one more time. And then this is going to look better. So that's what burn-in does. You can't choose burn-in to be longer than the number of points in your chain because that means you're throwing away your entire chain. There's nothing left to see. But now things look pretty good after I've thrown away the first 70 points. Any other questions on burn-in, what this means? Please raise your hand. Please ask.